Hello everybody, it's my honor to be here and to have opportunity to present part of my research under the umbrella of this mini symposium that is honoring the work of Professor Giovanni Solari. Also, I've been having great time in Florence so far, and I'm looking forward to the rest of this conference. My today's research will be on the investigation of downburst-prone environments in Canada, where we looked into diagnostics of downburst using various machine learning models. The work that I will present has been entirely conducted by my PhD student, and I'm here because he couldn't attend this conference. So, previous presentations, I believe, gave really nice motivation for our work, but to give additional motivation, here we recently published a paper on the amount of insured losses in Canada caused by various types of wind disasters. And in the period 2008-2021, Canada experienced over 7 billion catastrophic wind loss from various windstorms. And we only analyzed catastrophic wind losses. That means loss per event is over $25 million. So only significant one. Now, here are some of the examples of losses being caused by convective storms on top left, winter storms, tropical cyclones, as well as tornadoes. If we keep this classification of wind systems, then we concluded that in Quebec and Ontario, blue and red respectively, convective storms govern the overall loss. Tornadoes resulted in the largest loss per event, but there aren't that many tornadoes. So accumulated over several years, we end up with convective storms being dominant contributor to loss. Now, convective storms, most of the wind related to convective storms, thunderstorms, cumulonimbus clouds, are downbursts. Now, downbursts can be microburst, macroburst, burst swats, different types of wind events, but here we lump them all together as downbursts. So, the question was then, when we got this result, is it possible to diagnose the occurrence of downbursts or convective storms, severe convective storm winds, using some sort of combination of meteorological variables? So we are not talking about forecasting. Forecasting is integrating some equation with time. We're talking about taking various variables, manipulating them in a statistical way to see if we can give a diagnostics of a downburst. And my student used various machine learning methods to do that. First, we have two sets of data. We have downburst data, and when I say downburst, I really mean damaging downbursts, because these are the ones that entered NTP, Northern Tornado Database Project, hosted by Western University. It's really excellent resource to use. So that's a downburst class. And then we have non-downburst class. That's CLDN data, that's Canadian Lightning Network. So we can go into database, see when we had lightning, and thunderstorms are the only clouds that can produce lightning. And we can see if that particular event was not associated with damage. Well, that's not non-damaging downburst. Now, for each of these two classes, my student looked into meteorological data. He looked into reanalysis. ERA 5, latest ERA 5 analysis. He did some quality control, and then using the ThunderR package developed by Professor Mateusz Tezirski from Poland and his colleagues, we calculated a number of so-called instability parameters, 38 or something like that. And these instability parameters are then assigned to these two classes. Now, the entire data set was split. 100% of data was split into 80% of training and 20% for testing. And then on the training data set, the student looked into various machine learning models, how they perform, and also looked into different resampling methods, which I will talk a little bit more about in the next slides for the reasons that will be very clear in next slide. And then after training models, various resampling methods, we would test them against the remaining 20% of data. Why is resampling necessary? Well, this is the common problem when one is analyzing extreme events of any sort. We have Downburst class that has 306 samples over this period 2019-2023. And non-downburst, again, non-damaging downburst class is over 19,000 data. So it's a big imbalance. So minority set is much smaller than the majority set. And now there are various techniques how to address that. One is to increase the number of downburst class by resampling. Another is to decrease the number of non-downburst class entries, combination of these and so on. And we tested many, but I'll just mention one because this one ended up, as you will see, being the most effective. It's called smooth or synthetic minority oversampling technique. The idea is we have in a variable space, we have a downburst event and we find k neighbors, randomly pick one, and then you draw a line between these two, and from that line you randomly pick another event that could be your resample. And now you can already imagine there could be a million modifications to this method, and there are a million modifications in the literature. How many k neighbors? Should it be straight line? Should it be completely random? And so on. At any rate, these 7 machine learning models were tested with many different resampling methods, and as you will see, the random forest machine learning model ended up being the most accurate. Lastly, in terms of methodology, well, not lastly, but I told you we calculated various parameters. These parameters we classified into the so-called parcel parameters, what one can estimate from thermodynamic diagrams, kinematic parameters, thermodynamic parameters, and composite parameters, which are some sort of linear or nonlinear combination of these other 3 groups. Now, when one is dealing with binary problems, then it's useful to construct a confusion matrix. When we have true positive cases, that's when the downburst occur. Again, damaging downburst, always think the damaging downburst occur model said it's going to happen. Then we have false positive, model said there is going to be downburst, observation said it's a sunshine and rainbows outside. True negative, there was no downburst in both model and database, and false negatives, which is basically the worst, when the model said there is no going to be damaging downburst, but yet one occurred. And now there are various quantitative matrices, metrics how to assess performances of these models. One is Matthews correlation coefficient, which is generalization of Pearson coefficient to these binary data. Critical success index, which is very good parameter for unbalanced data sets, because as you can see, it doesn't take into account true negatives. And in types of problems, in types of problems where you have extreme events, true negatives really dominate. If you ask me, what is the weather going to be like in Florence tomorrow, I can always say it's going to be sunny, and most of the time I'm going to be right. But that's not the point, because there are many true positive. We want to know when it's not going to be sunny, like maybe tomorrow, by the way. And then there are some other scores. ROC curves are very well established mechanism to assess accuracy of the model, where you plot false positive predictions versus overall accuracy of the model, and so on. What we see here, this is a busy graph, but I'll try to guide you through it. 3 different rows are 3 different evaluation matrices for machine learning models. They all range from 0 to 1. X-axis is different resampling methods that I mentioned, and then different curves are different machine learning models. You can, first of all, it's very good news that pretty much all models follow the same trend. That gives some sort of a confidence for our analysis, but fortunately some models are doing better than others. So you can see that certain resampling techniques are really bad. They actually decrease accuracy of our results. But as you can see, the particular variation of this smooth technique coupled with the red curve, which is the random forest model, provides the best accuracy of our diagnosis of severe downbursts. We can see that compared to base case, when no resampling is used, our accuracy is increased for about 0.2 units, which is significant. Now here is another example of assessing accuracy of our model. So what I perhaps forgot to mention, the resampling was done 1,000 independent times. So it's like Monte Carlo simulation to see variability of the predictability of our model. And here you see these box and whiskers plots. So the dotted line is median of these 1,000 simulations. And you can once again see that the one model for various matrices, one model is separated, and that's again a random forest model. Now you can see that this matrix area under the ROC curve tends to be very good for all models, but the reason is the following. This metric is very often used in statistics, but it's really misleading in terms of extreme events where we have, so the x-axis is false positive divided by false positive plus true negative. True negative dominates, and therefore you get very small number because it's in denominator. And then on the y-axis where you have also very small number because true positive is high, you end up with the area under the curve pretty much always being high. But that's because if you guess that it's going to be sunny every day in Florence, your guess is pretty good. So here is much better performance of the model based on the critical success index. In short, the best models perform in the top right corner of this diagram, and once again you can see that the random forest model is the best performing model. The dotted curves are very interesting because then they indicate the amount of over-prediction or under-prediction a model. So our model over-predicts severe downburst for about 1.2. Here are another measures of the validity of the model, precision score. Precision score is very interesting because it measures how much model is pure. If model detects, let's say there are 100 downbursts and the model detects only 10, then you can be pretty certain that these 10 are really downburst. You didn't make any mistake. Whereas recall score measures overall how good model captures. So if you have 100 downbursts, it will identify maybe 200, but you captured all of them. And F score is just a combination of these two. So in the case of severe wind events, it's really necessary to have high recall score because we would rather have false positives than false negatives. False positives, you say it's going to be tornado or downburst, nothing happens, okay, people are maybe not happy, but there's no damage. In case of false negatives, that's the problem. And I will finish with this analysis that we performed. It's called permutation variable analysis. So as I said, we tested models for various meteorological variables, and the student wanted to see which of these variables are most important in the diagnostics of downbursts. And here is a list of them. So he used backward multipass technique, which is when the model has all variables, let's say 5, and that's certain performance of the model. Then we remove one variable and see how much performance drops. Then we remove second, third, and so on. And we can see that the most important variable is CPS, cold pool strength, which is basically temperature difference between the outflow and the ambient atmosphere. DEI, I'll talk just briefly about it. It's an index that I proposed with few colleagues in another study for United States. Here is forward multipass filter. Okay, I'm going to skip it for the sake of time. But we also performed this using analyzed performances using these different matrices, not just AUC, but various modifications. And we always basically see that cold pool strength is a governing parameter, which is very good because it's simple parameter and can be obtained from numerical weather predictions. DEI was proposed recently by the second author, Mateusz Stazarek. Although I'm the first author, it's not me who came up with this idea. It's a parameter that combines CPS and maximum wind shear. You see, you managed far in science when you introduce abbreviation to abbreviation. So W max shear is abbreviation, but it was too long, so Mateusz introduced yet shorter abbreviation. But anyways, this parameter performed really well in the United States, and we see now in Canada it is pretty good diagnostics parameter for severe downbursts. I will skip this. So what is next? There are two things that are next. First, as you can see, what I presented here are bulk results, just to see how good various models perform. What the student is working on right now is to pick particular case study when damage occurred, let's say 17 July 2021. How good our methodology would alarm us about that damaging downburst 1 or 2 hours in advance. And the second thing he is working on is trying to replicate these results, but using what we call traditional methods, not machine learning, but simple statistical regressions to see if we can get similar results, but not using convoluted machine learning methods. So with that, I'll put summary that windstorms are the most disastrous weather hazards in Canada, that out of these, convective storms govern the losses. Machine learning, there are many different models we tested and resampling methods. It turned out that random forest with a particular support vector addition to smooth method is the best suited for this type of analysis. And these are the parameters that are most important in the diagnostics of severe downbursts. Thank you.